Hello and welcome to Video Lecture 18. Video Lecture 18 covers diodes, transistors, and two other interesting circuit configuration elements. This is the last of the new material in this course and the last of the material in Unit 3. So, essentially in Unit 3 we've covered four topics: dependent sources and op-amps, which we've done in the last two lectures, and diodes and transistors today. As we start looking at our material today, we consider the linear circuit current voltage characteristics. So before we even think about diodes, transistors, or any other element, we recall that we start off with the concept of a black box, and in that black box we can always identify the circuit behavior. In this case, we literally consider the situation where we have a black box and there are two nodes, the nodes A and B, and we're going to give two copies of this because we have two standard ways of defining what's inside. We know that for absolutely every linear circuit, we can identify what's inside this black box simply by giving an equivalent circuit, either a Thevenin equivalent circuit, which has a resistor and a Thevenin voltage, or a Norton equivalent circuit, which has a current source and the same equivalent resistor. We also know that there's a standard relationship. VTH, the Thevenin voltage, is equal to the Norton current IN times that equivalent resistance. So the relationship follows Ohm's law. When identifying the Thevenin voltage, we simply look at the open circuit voltage across the terminals A and B. We measure the voltage and then we know what that black box contains. On the other hand, when we consider the Norton current, if we want to identify that, we short circuit the two terminals A and B. That identifies the Norton current for us, and realize that as we short circuit that, the reason that identifies the Norton current is because the equivalent resistor is bypassed entirely, as current will always go through the path of least resistance. By calculating the voltage and the current, we are able to understand something very critical. We are able to understand the current voltage characteristic of the circuit. And of course, as I said, in a linear circuit, that's a very straightforward characteristic. It always follows Ohm's law. So that's something that we understand, and we know that with a linear circuit, all we really need to know is Ohm's law. Now, we're going to take this information and use it to understand a nonlinear circuit. And when you do that, what you really need to realize is the current voltage relationship defines everything that we need to know. And everything inside that black box is linear. And so that what's inside the black box will follow Ohm's law, and we can simply attach a nonlinear element to it and still understand it by understanding what happens within this basic relationship. So, to understand what happens here, let's consider the nonlinear diode. We start with our same black box. We have A and B, and inside of here we have a supply current. And instead of attaching our standard linear element, we're going to attach a nonlinear element, also known as NLE. In this case, the nonlinear element that we're attaching is a diode. The symbol for a diode is a triangle with a line over it, and notice that when you do a diode in this way, you have a current that goes essentially in the direction of an arrow. When you attach that into the circuit, you want to understand what happens. So you're putting it into your basic Thevenin circuit, putting in your diode, and seeing where things go. Now that's pretty straightforward. We have an equivalent resistance, we have a Thevenin voltage. If we short-circuited it, we know that the current would go in this way. The diode will allow that to go, but you have to understand that the diode will also have current voltage characteristics. So let's consider the diode, and then we'll see what happens when we place it into a circuit. There are different diodes, but basically a typical nonlinear diode characteristic will look something like this. We have a voltage and we have a current, and we're going to be comparing voltage to current. And it'll have a region that's pretty flat, and then it'll move and flatten out in that way. So this is one type of nonlinear current voltage characteristic. And it's clearly nonlinear because it's not just a straight line, it has a curve, it flattens out. This curve completely describes the diode response. So what that means is that if you choose any given current, let's say you've got this current, and that's the current you put through the diode, the voltage across the diode will be the voltage that intersects based on this curve. And so you can completely understand what the voltage is going to be when a particular current goes through the diode, and everything is described entirely by this current voltage graph. Sometimes it's a graph, sometimes it's an equation, but this will explain what happens within the diode itself. So how does that help us, and how does that connect to everything else? We start with a black box. The black box is our supply. We attach to it a nonlinear element. These two are connected through two terminals, the terminals A and the terminals B. And we can look at what's inside the guts of each of these. On the left in our supply, we're going to assume a Thevenin supply. We could equally assume a Norton supply. It doesn't make any difference. Here's our Thevenin voltage. Here's our equivalent resistor. Then we connect to it a diode. Note this is exactly the circuit we had before. Well, we can consider the behavior of each of these, and that will completely explain what's going on. So let's start with the behavior of the supply. The supply has linear current voltage characteristics. Let's look at what these are. Well, here's our voltage, here's our current. We know that when we have an open circuit, then we have no current running through. At the open circuit, I is equal to 0, V is equal to VTH. We also know that we have a short circuit. At the short circuit, we connect a wire. When we connect a wire, V is equal to 0, and I is equal to the Norton current. Draw each of these into our graph. Here's the point where the current is equal to 0, the voltage is equal to VTH. Here's the point where the voltage is equal to 0 and the current is equal to IN. Connect these with a straight line. This is the characteristic of the supply. And the supply always has to follow this characteristic because it's a linear circuit. Everything is connected with a straight line. Now let's consider the nonlinear diode for a minute. The nonlinear diode has a characteristic that looks like that. We've already seen it on the previous page, and this is particular to the diode that we are assuming we're using. As I said, not all diodes look the same. They can have equations, they can have graphs. Regardless, you will always put the graph down from the equation. They don't always look the same, but they have a nonlinear characteristic. So this is our particular diode IV characteristic. Now, if we've connected these two things together, what you have to understand is that by connecting them, the diode operates in the way that it operates. It can't change. The supply operates in the way that it operates. It can't change. So by putting this diode into the circuit, there's only one spot, also known as the Q spot, or the Q point rather, where the operation can actually work. So this is going to be the current and the voltage that operate when we connect the diode. And so we can understand right away exactly what's going to happen in this circuit. We're going to have VTH. We have REQ. The current that goes through here is equal to that current when we have placed that diode. The voltage drop across the diode is equal to that specific diode voltage drop, and we end up with a Thevenin, with a Kirchhoff's voltage law, which tells us that VTH minus ID times REQ minus the voltage across the diode is equal to 0. So that'll tell us exactly what the drop is. Notice that that has to happen. This equation is going to work out specifically because we found the point of intersection in this graph, and that is the point that makes this equation work properly. And this is how a diode works. Essentially, a diode has its own nonlinear characteristics, and they force the choice of the current and voltage through that circuit, and we can find the equivalent behavior of the circuit in this way. So it's kind of neat because it's a little bit different from what we've seen before. We work with Kirchhoff's voltage law, which has to work despite the nonlinearity. We recognize that within that, our nonlinearity is identified by the voltage drop in the diode, and also in a sense by the choice of current, because those two elements relate to the diode. But those two elements are going to be dictated by how the circuit operates, and they're going to be dictated by the diode characteristics. And yet Kirchhoff's voltage law is going to have to work because it always works. That's the way a circuit operates. It follows Kirchhoff's voltage law. So this is kind of neat, and it gives us some ideas of how we actually work with diodes. So this is the idea behind a diode. A diode is a circuit element that forces current in a particular direction, and it only allows current and voltage to match based on its own characteristics. So it, in essence, forces a particular type of current based on the setup of the linear circuit it's attached to. So generally, as I said, this is how a diode works, and we essentially can have different diode characteristics. So let's draw a few diode characteristics. There's the type that we just saw. So that's diode number 1. And I'm going to draw you a different type, diode number 2. The type we just saw is a curve like that. Sometimes there's actually jumps where things can go up and down. So that's another potential diode characteristic, and one that is sometimes found in certain diodes. So with a diode, you have a nonlinear graph. The graph shows what happens, and if you want to identify what happens to the diode, you have to understand the circuit you attach it to. Let's say we attach each of these two diodes to circuit number 1, in which we have Norton current number 1 and Thevenin voltage number 2. We draw the line that connects these together. That's the linear characteristic of our circuit. We identify the Q point, and this is going to be the diode voltage and the diode current when we connect that diode into that particular setup. If we had a different Norton current, let's say this is our Norton current, let's say this is our Thevenin voltage, we would simply connect them together. In this case, it made it look like it's in the same place. It doesn't have to be. It can be somewhere completely different. That would be our new Q point. And of course, this is completely dependent simply on the current and voltage setup in our actual circuit. So let's say here's our Norton current number 3. Let's say here's our Thevenin voltage number 3. Notice that these will come at a completely different spot. And that is our Q point for circuit number 3. So you identify I Norton in your circuit. You identify the Thevenin voltage in your circuit. Notice that those are related by the equivalent resistance, where the equivalent resistance can also be found by taking the voltage over the current. And then you intersect your diode IV characteristic with your supply IV characteristic. The point of intersection is your Q point. And Ultimately, the punchline in this is the circuit will operate based on the current and voltage at the Q point. So if you want to know what those are, you simply take a look at each of your different points. So in our third circuit, this is our diode voltage, and this is our diode current. In our second point, it was almost on top of the first one, so I didn't sort of draw it in separately. But let's call it this point and pretend it's slightly different. And you simply do that. And of course, it's important to realize that the operation is dictated by two things: the voltage current characteristic of your diode, and also quite separately by the actual characteristic of the supply, because those two lines have to intersect. So let's look at diode number 2 and just do the same thing for diode number 2. Let's say here is our Norton current for our first circuit. Here is our Thevenin voltage. Connect the line. Note something interesting happens in this particular diode. In this particular diode, there are 3 possible operating points. So that's something important to realize, that if you have a nonlinear diode that moves with going up and down with more than one possible point of intersection, whatever your closest current voltage relationship is to where you started off is the one that's going to hit, and you actually just hit a stable point. That's where you're going to end up. Notice that in this diode, that's not always the case. If your Norton current and your Thevenin voltage are a little bit further off, then you might only hit one operating point. Or if you have a Norton current that's in there and a Thevenin voltage that's in here, you also might hit only one that's earlier on. Any of these are valid. They all simply depend on the intersection. Note that for each of these examples, there are 3 possible supplies. Those 3 possible supplies each come up with their own Q point. And that's how a diode works. The next circuit element that we are going to consider is the transistor. The transistor is most commonly used as a switch and is often the guts of digital circuit elements such as gates. The transistor is a 3-terminal element where the different terminals allow for a control of what happens within the different currents and voltages, which is why it's often used as a switch. There are different kinds of transistors. They're not always built the same way, but essentially they all have the same basic internal structure. Transistors are made in integrated circuits with different doping, and the substrate physics describes how they actually work from an electron point of view. But we don't look that deeply. We look basically at the structure and the currents, and we realize that these are interesting elements because they're nonlinear elements, and the way that they behave actually changes, and they have different properties at different times. Now, there are 2 common types of transistors: the BJT, also known as the bipolar junction transistor, and the FET or MOSFET. MOSFET is a type of FET. There's a JFET and a MOSFET and others, which is called the field effect transistor. The key characteristic of the BJT is that it is controlled by current, whereas the key characteristic of the FET is that it is controlled by voltage. Let's take a quick look at these circuit diagrams. They're similar but not identical. And after we do that, I'm going to note that we are going to be only looking at the BJT in detail. The BJT is often drawn with a base, which then has angular lines coming off of it, a collector, and an emitter. To the left, the base is the controlling current for the actual transistor. The collector is on the top. Current goes down from the collector, and the emitter is on the bottom. Current goes down through the emitter. Notice that I just drew what's known as an NPN transistor, and actually the other way around changes the direction of the currents in the emitter and the collector. The FET is similar in structure, except instead of having an emitter, a collector, and a base, it has a gate, a source, and a drain. Typically drawn in this way. You've got the gate, the drain, and the source. And often you also have a base drawn in, but the base is typically tied to the source. So this is the circuit diagram for your FET and the circuit diagram for your bipolar junction transistor. Notice that I drew an NPN in the bipolar junction transistor, and that's the one that we're going to be considering. In each of these, the arrow can be changed in the other direction, and that arrow simply depends on whether you started with an NPN or a PNP. Those are the way that the substrates are doped. Now, transistors are made on an IC substrate or an integrated circuit substrate through a process of doping. And there are basically two types of processes or two types of setups that are used for the configuration. One of them is called PNP and the other is called NPN. And it's important to understand that each of these create a very similar transistor, but the transistors operate in an opposite manner. NPN is typically created by holes, and those are the primary charge carriers, whereas PNP is created by electrons that are the primary charge carriers. The nuances of how they are created are not necessarily so important for you guys, but what is important to understand is the basics of how they work. So we will be looking at NPN transistors later, but I'm going to give you a basic rundown of these. The NPN transistor has the following diagram, which is exactly what we saw in the previous slide, where we have the base on the left, the collector at the top, and the emitter at the bottom. And we notice that the arrow specifically is pointing away from the base. Now, when we do that, we end up with a structure where we have the following chart. We have the voltages, and we're going to go through where each of these are later by looking at it, but we've got the voltages, and we've got the action that happens with these. Now, there is basically a voltage at the emitter, a voltage at the base, and a voltage at the collector. If the voltage at the emitter is less than the voltage at the base, and that's less than the voltage at the collector, then this works in a mode called active mode. If, on the other hand, the voltage at the emitter is less than the voltage at the base, but the voltage at the collector is greater than that, then this works in a mode called saturation. If the voltage at the emitter is greater than the voltage at the base and that is less than the voltage at the collector, it works in a mode called cutoff. And typically those three upper modes are the only ones that you would want a transistor to work in. Now, it is also possible that the voltage at the emitter is greater than the voltage at the base, is greater than the voltage at the collector. In this case, this transistor works in something called reverse mode. Now, the only reason that we're talking about this at this point, we're going to explain each of the upper three modes in detail and talk about the reverse mode briefly. But the only reason we talk about these at this point is to give you an understanding of the importance of knowing whether you're using PNP versus NPN. So that was for NPN. That's the type of framework that we're usually going to have. On the other hand, we've got PNP. If we're working with PNP transistors, then all of this works slightly differently. In that case, in the first place, if VE is less than VB is less than VC, we work in reverse mode. If we have the emitter voltage less than the base voltage, but the collector voltage is less than that as well, then we work in cutoff mode. If VE is greater than VB is less than VC, we work in saturation mode. And lastly, if we're at the situation where the emitter voltage is greater than the base voltage, which is greater than the collector voltage, we are in active mode. Note, we'll just tweak this a little bit, that in each case you never really want to be in reverse mode. Now, what does all this mean in practice? It really talks about the direction that the currents are flowing. So if you have a base and you have a PNP transistor, then you'll notice that the symbol has the opposite direction for the arrow. What that opposite direction means is that the current is flowing from the emitter upwards through the collector, as opposed to the NPN where it flows from the collector downwards to the emitter. Now, like I said, this depends on the application. It's a nuance, and it's really important only to understand generally how a transistor works as a switch, not the difference between these. But I point it out because if you're ever practically building something, you need to be very aware of which of these two transistors you're using in your build. And with that, let's take a look at how the bipolar junction transistor actually works. So, to recap, we have a base. That base has a current running into it, and that current actually controls the flow of current in the entire transistor. We draw the transistor this way with the collector on top, the emitter on the bottom, and we're using an NPN transistor, so the arrow points away from the base. When we have this transistor model, we have a current in the base, we have a current in the collector, and we have a current in the emitter, and we use Kirchhoff's current law at the node in order to understand what's happening for each of these. Now, this bipolar junction transistor has three main ways that it works. It's either in active mode, where it works in a traditional manner where we consider the base voltage to be a control variable, the base current to be a control variable, and that will control the equivalent of a dependent source current coming from the collector to the emitter. So that's the active mode, that's the main mode. Now, if that base current happens to equal 0, we talk about this as being in cutoff mode, which means that basically it's still off. And on the other hand, if that current is so big that it maxes out the amount of current that that actual dependent current source is able to create, it becomes in saturation mode. Just like a dependent source, we are going to prefer to be in active mode, and we end up being in one of these three modes, and we try to see if active mode works, test the variables, and if that doesn't work, then we realize we're either in cutoff or saturation. The last point is that if we've managed to create a scenario where those currents are backwards from the emitter and the collector, then we're in something called reverse mode, and that's not a good place to be for a transistor. It's possible to use it that way, but I'll explain later why that doesn't work out well. So let's look at each of these three modes in order to understand what they actually do. So we start with the cutoff mode. The cutoff mode is the point in time when the transistor is basically off. So when you talk about a transistor, you have your basic model, your base, your collector, and your emitter, and there's a current in the base. The goal is for the current in the base to control a current in the collector. If the current in the base is equal to 0, then since the current in the collector is going to be a scalar multiple of that, the current in the collector becomes 0 as well. Now, if you want to model this with a basic circuit diagram, well, you've got your base and it hangs. It creates an open circuit between all other points. You have a collector, it hangs, and you have an emitter and it hangs. There's no connection between these, so there can pretty much be any voltage across any of these that you want because they act as an open circuit and there's nothing that you can do with them. And when you're looking at that, you simply have an open circuit. It's not a very interesting place to be, but it is important because as you're using it for a switch, this is the position where the switch is off. Next, we have the active mode. The active mode is the traditional mode in which a bipolar junction transistor operates. So again, you start with your basic model. You have your base, your collector, and your emitter. And again, we're in the NPN, so we're going downwards. You have a current in your base, but this time that current is greater than 0. When you're in active mode, that current creates a current through the collector, and that current through the collector is measured as a scalar multiple of beta times the current that's in your base. You obviously then have a current in the emitter, and that emitter current is actually just equal to the sum of the two currents through a Kirchhoff's current law. So that's just beta plus 1 times IB. The important thing in these two is the relationship between the collector and the base current. And also, in order for this to happen, there is a particular fixed small voltage that goes across the base to collector, and that's typically measured as V alpha. So when these two things happen, your actual transistor is in active mode. If you want to model the transistor in active mode to understand what that looks like, then you model that with the base connected to a battery. That battery has a value of B alpha, and you have your collector going through a dependent current source. That dependent current source has a current going through it of beta times IB, where IB is the current in your collector. And of course, there's one node there, and the emitter goes down below. Notice there's no voltage across your emitter from that middle node. The two places where you have voltage are in your dependent current source and in your battery. And this is the model for what happens in the active mode. And whenever you know that something is in the active mode, you can use this model. In fact, this is also helpful because when you do any analysis on a bipolar junction transistor, you are going to pretend that this is the model you're using, and then you're going to test the values. And if the values work out right, then you see that you're in the right mode. And if the values are problematic, then you're not. The active mode is the traditional operational mode of the BJT in this way, unless you're specifically focusing on an operation which goes between cutoff and saturation. Lastly, of the three modes where you want your bipolar junction transistor to operate is the saturation mode. The saturation mode is simply the point where the current through collector can get no bigger. So you start with your base, your collector, and your emitter. You have your current in your base, and you have your current in your collector. But the current in the collector can never get greater than a maximum ISC or I of source. So this is basically the maximum current that the source is able to accommodate. So if IB gets big enough that you can't make IC equal to beta times IB, you end up getting stuck and having this maximum value. Now notice that in this case, you consider the voltage from the collector to emitter to equal 0, and the voltage from your base to your emitter to equal V alpha. So if you were to do a model, those are the two equations that matter. Those are the two that are going to be most important in terms of doing your model. And if you wanted to actually model this with a circuit diagram, then you end up having a battery in the same place that you had before. And with that battery, we have a connection from C to E that is direct. The voltage from C to E is equal to 0. The voltage across that battery is still V alpha. But in this case, we notice that we have a fixed amount of current coming through here. That current is equal to ISC. And we don't model it with a source directly because, as we'll see later, that ends up being directly modeled and forced by other components in the actual circuit. The last mode that a bipolar junction transistor can operate in is the reverse mode. When operating in the reverse mode, although we have an NPN transistor that works in its typical manner, we actually have a current that is flowing upwards instead of downwards. You could model that with your dependent source going this way, and we're going to call it beta active times IB, and model that in this way. But the one thing that you have to realize, When doing this, so when you're in reverse mode, beta is much smaller than, so beta of the reverse mode is much smaller than the typical beta. The operation is not efficient. It's not set up physically in order to operate well this way, and that's not ideal and not what we want. But there is this reverse mode. It can happen, and that's just something to be aware of. So the last thing what we're going to do when we look at our transistors is we're going to take a look at the currents and the voltages around a typical transistor circuit and how this typical circuit is set up. So we start with our transistor. We have an NPN transistor. We've got the base, the collector, and the emitter set up. Now, when you use a circuit like this, you're going to want to hook up a voltage to your base. That voltage to your base is the source voltage, and that ultimately controls what the transistor is doing. Your emitter is going to be connected to that. You can consider a ground at the bottom. And on the collector side, you have a collector resistor, so we're going to call this our base resistor, our collector resistor, and we have a bunch of batteries. Notice that I label these as batteries and not as a general source because this is the power supply to my entire circuit. So we need to show that we've got a power supply in our setup. This is what it is. And this dictates the maximum source voltage. Typically, there's some standard ranges for the numbers. Beta, when you're in active mode, is going to be typically between 50 to 2 to 300 or so. And 100 is a very, average value. V alpha is typically under 1 volt. We'll often see numbers like 0.7, for example. Now, what are each of the components of this circuit? VC is the power supply. This is our NPN transistor. VS is our input. And our output is the voltage across the collector to the emitter. So this is the typical pieces that we're looking at in here. And when we analyze this circuit, we're going to need to analyze a KVL where we have the voltage across our inner input loop and the voltage across our outer control loop, our outer supply loop rather. So when we take a look at this, here's the things we need to know. The transistor acts like a switch. So the transistor acts like a switch, and that's the purpose of using a transistor, is that they are switches. How does it act like a switch? Well, it has the following characteristics. When the source voltage is less than V alpha, the bipolar junction transistor is in shutoff mode. When the source voltage is greater than V alpha, the bipolar junction transistor is in active mode. Now, the bipolar junction transistor will be in active mode, and the current that goes through the collector down to the emitter is going to always try and be beta times the base current. But that's only going to fly as long as there's enough power to supply that. So, when IC is equal to ICS, which is just that power supply divided by that resistor, no more current is capable of flowing. When that happens, the BJT saturates. So again, if the source current or the maximum current reaches VCC over RC, you're in saturation mode. And at this point, it's fairly straightforward to actually analyze the circuit using a KVL or the mesh currents in the BJT itself to understand what's going on. A few things to note. Here's some typical values. VCC or the power supply, is typically about 5 volts. Beta is typically about 100. V alpha is typically about 0.7. The resistor near the base will typically be on the order of 100 kiloohms, so that needs to be a large resistor. And the resistor on the collector will typically be about 1 kiloohm. Now you want the resistor near the collector to be reasonably small because the maximum current is dictated by VCC divided by RC, so you want to make sure that that isn't too large of a resistor. The larger that resistor, the smaller the maximum current can possibly be. So you'll note that maximum current is VCC divided by RC. So the smaller RC is, the larger VCC is, the larger the maximum current that you're going to have is. And you would typically want this to operate in active mode. And so this is a transistor. It's just a flavor of it. We're not going to be looking at the actual computation. We just want to understand the basics. The diode and the BJT are really the opening to the next area of what happens in electric circuits. And they become more complex, and what you do in terms of computations is also more complex. Now, the diode and the transistor are by far not the last types of circuit elements that there are. And we're only going to talk to you about a few more just so that you get an idea of some of the things that you can see, but we're not going to go through any numbers or anything else. The next thing that we're going to talk about is coupled inductors. We know that we have inductors. Every inductor has an inductance L, and that's created by having essentially a magnetic field and current, and one induces the other. They create a differential equation. When we have mutual inductance, where you have two inductors that are coupled together, then you can label one of these as L1 and the second as L2. And you can actually talk about the relationship between the two inductors because one inductor will actually cause a relationship with the other one. When you look at this, if you talk about your first inductor, it has a voltage V1, and your second inductor has a voltage V2. Because the couplings are connected, the inductance is connected, and so the actual currents from one side will cause a relationship in the other. We call the mutual inductance M, and we state that V1 is equal to L1 di1 by dt plus or minus M di2 by dt, and V2 is equal to M di1 by dt, now that can be plus or minus, plus L2 di2 by dt. Now I just mentioned that this can be plus or minus. How do we know which one it is? Every coupled inductor will have a pair of dots. If the pair of dots is on the same side, then there is a plus sign between each of these. If on the other hand, the pair of dots is on opposite sides from each other, you're going to have a minus sign. And you notice that the differential equation for V1 connects the currents that are in I1 and I2 through that differential equation in order to understand what's going on. Same thing with V2. The two different differential equations are connected. And so with this, you understand that there's a coupling. There's actually a relationship between these. Now, how closely the coupling works really depends on the structure. When you have the coupling where the coupled inductors have a maximized magnetic coupling, you have something called a transformer. A transformer is usually signified by inductors with a line between them or a pair of lines between them, and you know that the windings have a relationship where N2 to N1 tells you the ratio of the windings. That ratio is also equal to N. Now, the reason that you would do this is very simple. So this is a device where the coupled inductors have maximized magnetic coupling, and the purpose of this is very simply to change voltage and current levels. So you may think about, times when you travel and you're going to a country where the outlets have different voltages than the ones that our stuff is used to, and you have to make sure that the power doesn't blow the circuitry inside, and you might bring a transformer with you. The whole purpose of that transformer will be to change a 120 volt plug to a 220 volt plug, or a 220 volt plug back down to a 120 volt plug. Note that when those transformers do that, they don't change the frequency, they only change the actual voltage. And in fact, a transformer does that. So with a transformer, if you have this maximized magnetic coupling, the voltage in 2 is going to equal plus or minus n times the voltage in 1, where here you have the voltage in 2, here's the voltage in 1, and you have this exact proportion, and the current in 2 is going to equal minus or plus 1 over n times I1. Notice that the difference between that plus or minus is simply the direction that you set these up in, and the direction basically of which they're going to be maximized. So these are the two equations that you get. Sorry, just rearrange them slightly. And this is a transformer. So this is another very interesting thing that you can do with a different circuit element. The last thing that we're going to talk about is a bridge circuit. In a bridge circuit, you have a voltage source and you have a diamond setup. Sometimes these can be pure resistances. Sometimes these can actually be sinusoidal, and then you have impedances. So we'll label them as impedances. So you have impedance Z1, Z2, Z3, and Z4. And then you have voltage points A and B. With a bridge circuit, you will also have an impedance between points A and B. Now, this is a setup where you can use inductors, capacitors, resistors, and typically you're going to be using linear elements, and you want to understand what to do with them. Bridge circuits on their own, or a single bridge, are fairly straightforward to solve. You just need to have the right perspective to solve these. To solve a bridge circuit, you can treat the bridge or the circuit that's in the middle, so this is the bridge, our loading circuit, as the load of your circuit. So to solve a bridge circuit, treat the bridge, which is ZL, as the load. It's important to realize that redrawing things can often give us a good perspective on exactly what goes on. So if you're going to redraw that, here's point A, here's point B. And you notice that from A to B, you have essentially a path from Z1, Z2 to B, or a path from Z3 to Z4 to B, or of course the load, which I'm separating out at the other end. So if we redraw the circuit so that it's in a configuration where it's more straightforward to follow, we have Z1, Z2, or Z3, Z4 being our two parallel paths, and of course in between these we have our source. Once you set it up this way, it's quite straightforward to use superposition. Let's just draw that slightly more neatly. It's quite straightforward to use superposition, KVL, and KCL to calculate. So use superposition and KVL and KCL to calculate VTH and IN, REQ, and you can figure out what you're doing from there in order to solve this bridge circuit. So this is technically not another circuit element, it's a way of using a circuit. The equivalent resistance, by the way, or the equivalent impedance if you're working with impedance, is equal to Z1 in parallel to Z3 plus Z2 in parallel to Z4. Let's just write down that that's ZEQ. And this is just, the last little something to think about. It's another framework and setup for what you can do. And this concludes Unit 3, and this also concludes our electric circuits course. So in Unit 3, the main things we've covered are dependent sources, op amps, diodes, and transistors.